focus again, and now we'll go. Okay, so A is a U by V matrix. U and V are positive integers with rational entries. Okay, A is image partition regular over the set N of positive integers, which is written IPR over N, if and only if, whenever N is finitely colored, there exists X with entries from N, as entries, positive integer entries, such that the entries, let's write this, the entries of AX are one colored, monochromatic. Okay, so for instance, you've got Schur's theorem. Says if you finitely color the positive integers that you can get X, Y, and X plus Y the same color. Well, that's the assertion that the matrix 1, 0, 0, 1, 1, 1 is image partition regular, because if you do that product, you could get X, Y, X plus Y. Okay. And that is an image partition regular matrix. And also, if you take Van der Waerden's theorem, well, there's a different matrix for each length. So let's say we want to talk about the length 4. You have the matrix with the rows 1, 0, 1, 1, 1, 2, 1, 3. If you multiply that by AD, then you get the image, which is A plus D, A plus 2D, and A plus 3D, and those images, and that's showing that this particular matrix is image partition regular. Now, I didn't say the image is in there because there's another notion which is called kernel partition regularity, a problem which was solved by Rado in 1932. Somewhat later, namely 1993, these guys, I'm one of the few speakers who actually knows how to write his own name. Anyway, Hindman and Leader derived a few characterizations of matrices that are image partition regular over N, some of which are computable. From this point of this talk, it's a somewhat later result that I'm interested in, and this comes from let's see, 2002. Okay, the Hindman and Leader again, along with Strauss. And incidentally, this, as in most of the stuff I do, this is a co-authored paper with Donna Strauss. And I didn't mention it, it's to appear in the integers memorial volume for Ron Graham. Anyway, we derived the following characterization. So again, A is a U by V matrix. The following are equivalent. A is image partition regular over N. B, for every central set C, there exists X in a to the v, sorry, n to the v, such that the entries of AX all come from C. Okay. And the third one, again, for every central set C, the set of all X in N to the V such that AX is in C to the U is central in N to the V. Now, I didn't say what central is, and I won't specifically. There are dynamical definitions. There's a dynamical definition and there's an algebraic definition. The crucial point here is that they're partition regular. That is, if you take a central set and you finitely color it, then one of the colors will be central. And so in that makes the B implies A here trivial, because one of the colors will be central, and that does that job. C is an example of a fairly common phenomena in Ramsey theory, and that is that one shows that something is non-empty by showing that it's big. This is sort of like at the end of last talk, talking about the probabilistic method. You know, show that something's not empty by showing it's moderately big, at least. That's what Furstenberg did in his proof of Semiramis theorem. That you take a set of positive upper density, and you show that it contains arbitrarily long arithmetic progressions by showing that the set of such starting points has positive upper density. And there are a few other properties of notions of largeness for N, which have corresponding statements. But missing from that is the statement about IP sets. So C is an IP set if and only if there exists, oops, can't run out of the screen here, if and only if there exists a sequence in N such that the finite sums from that sequence, which is to say the set of all sum over T in F of xt, such that F is finite and non-empty, that set is contained in C. Okay, so this is an IP set, and the corresponding statement is not true. That is to say, let's take a very simple example. Let's take the matrix, which you will recognize as the three-term arithmetic progression. Okay, this has no image in the finite sums of the even powers of 2. Now, I'm going to give you a proof of that. I like it. Actually, several years ago, I was writing a paper with Vitaly Bergelson, and we came up with the proof I'm going to give you. But in the intervening years, I forgot about that paper and forgot about that proof, and coming up with this example with Dona, had about a page-long proof of this condition, that condition, etc., to show that this statement, that it doesn't have any solutions. And what I'm going to give you is the old short one. So suppose you have a solution in there. So you're going to have A plus D, and A plus 2D. Okay, so A, as every integer, will have a binary expansion. So will D. Now, we're not asking that D be the same color, but D, I mean, in this particular case, that D be in the finite sums, but it's going to be that sum over T and G of 2 to the T for something. And A plus D is going to be the sum T and H of 2 to the T. And A plus 2D is going to be the sum over T and K of 2 to the T. And note that F together with H together with K has got to be contained in the even integers, because it's A and A plus D and A plus 2D, which are supposed to be in the finite sums of those even integers. Now let's let M equal the minimum of G. Okay. So when you write, so when you're writing G and D in binary, off to the right of M is all zeros. If M is odd, then M is an element of H. Because when you add A and D, the rightmost digit of D is not going to have any carrying. Well, that's impossible. So M must be even. But if M is even, then M plus 1 is in K, and that shows that in fact, does not have any solutions in there. Now, there's one problem with that example, and that is you will notice, well, it's still here, that this rank, if this matrix is A, then the rank of A is 2. The number of rows is 3. And it turns out that several of the results, not too surprising, depend on having the same rank as the number of rows. So we worked on that a bit, and I did an embarrassing number of proceeding with trying to go proof by cases. But let's take here the matrix 1, 2, 4, 1, 0, 0, 0, 1, 1. Okay, that has rank equals 3. And it turns out that that has no image in the finite sums of the 2 to the 4t. So the binary, all the binary positions are multiples of 4. Okay, I'm not going to, that proof is mild pain, but it's, anyway, it does show that even with the rank, you still end up with not everything is, and I guess I didn't define it. So let's say here, A is strongly image partition regular over N, if and only if, whenever C is an IP set, there exists X in N to the V such that the entries of AX are all in C. Okay. And so this is a matrix which has rank 3 and is not image partition, strongly image partition regular. I mentioned we got a couple, two sufficient conditions. This is assuming the rank is the number of rows. And for simplicity here, I'll just assume right now that the matrix itself is invertible. It turns out if your matrix, if you have a strongly image partition regular matrix, you can add columns to the right as you wish, and it's going to stay strongly image partition regular. So in any case, let's look at these things. So we're going to let A be U by U, rank A, rank U, so that means, of course, invertible. And let D equal A inverse. And let C1, C2, down through CU be the columns of A. If, and I'm only going to do one of the sufficient conditions here, but it's the one that contrasts very nicely with the necessary condition that we have. If there exists a non-empty I set of columns such that the entries of the sum of those columns are all positive, then A is strongly image partition regular over N. If A is strongly image partition regular over N, then there exists a set of columns such that the entries of the sum of those columns are non-negative. Okay, so that looks pretty close to an if and only thing there. Well, but let's look. It turns out that the sufficient is not necessary and the necessary is not sufficient. And let's go back to this example that we had. Now, it turns out any image partition regular matrix with 2 rows is strongly image partition regular. So we needed to go up to 3 to get this example. So this is the same one that I mentioned before. So here is A, and here is A inverse. And I do not have it memorized. I have to look it up. And furthermore, I was talking about this in Howard's seminar, and I think I wrote A down wrong. So when I wrote down A inverse, one of the participants pointed out that A times A inverse was not the identity. But I think if you want to amuse yourself for a minute, I think you can check. I believe this I am getting right for what is the inverse. Okay, so if you look there, you will see that the sum of the first 2 columns are 1, 0, 0. Okay, so that necessary condition is not sufficient because this is not strongly image partition regular. Now, as I mentioned, everything with 2 rows is strongly image partition regular. So, excuse me, if that is A, then A inverse is 2 minus 1 minus 1, 1. Okay. And you will see that the the sum of both of those rows, again, column 1 plus column 2, is equal to 1, 0. So the sufficient condition is not necessary. So in other words, you didn't get all of the entries positive there. Okay, now this is, of course, not everything that we have in the paper, but it's what I thought I could present succinctly. I see I am 5 minutes early, but fortunately, that gives somebody chance for a fast lunch. Okay.
Thank you very much, Neil. Are there any questions for our speaker? I am looking at the Q&A, and if not, then I thank Neil again. So we have